Tisztelt megjelentek, tisztelt akadémikusok, kedves vendégek, tisztelt Müller professzor úr, professzor Müller, kedves vendégeink. Akkor megnyitom a Magyar Tudományos Akadémia Fizikai Tudományok Osztályának rendkívüli ülését, amelyet abból az alkalomból hoztunk össze, hogy új tiszteletbeli tagunkat köszöntsük, és pedig egy rövid előadásban mutassa be a területének az aktuális állását, a székfoglaló előadása alkalmából. Berndt Müller professzor úr a magfizika, a részecskefizika és általában a modern fizikának egy nemzetközileg is elismert kiemelkedő alakja, iskolateremtő tevékenysége is nagyon fontos. Számos tankönyvet is írt, és nekem külön öröm, hogy most utána nézve a könyveinek felfedeztem, hogy nekem a polcomon ott van 1991-ben megjelent a neuronhálózatok fizikájáról írt könyve, amit akkor doktorandusz koromban akkor azt aktívan tanulmányoztam is. Úgyhogy számunkra külön öröm és megtiszteltetés, hogy osztályunk tiszteletbeli tagjaként üdvözölhetjük. Ugye a Magyar Tudományos Akadémia nagyon sok odafigyeléssel van a magyar nyelv iránt, viszont nyilvánvalóan racionális és megtiszteltetés okokból is nyilván az előadás angol fog elhangozni, illetve arra kérem Lévai Péter akadémikust, hogy a laudációt is már angol nyelven mutassa be.
Köszönöm szépen, elnök úr. And let me change into English just to say a few words about Professor Berndt Müller. In that case, you will hear what we are telling about you. So far, everything was very positive, and I cannot change this attitude. So, first of all, it is my pleasure and privilege to welcome Professor Berndt Müller and congratulate for him to become the honorary member of the Hungarian Academy of Sciences. Professor Müller is a very well-known, famous person of the high-energy nuclear physics, a big teacher. As President István said that you wrote a couple of books about high energy physics, theoretical physics. Also, they are on my shelf at home, and when I used to teach at the university many times, I go back to this. Seems to be oldish, but even in these days, completely true knowledge. Yeah, it's very important, and your books are very educative, and it's great to have it. You were working at the Frankfurt University, where you got your PhD, which was 1973. After the PhD, you moved to the US, to the Yale University and the Washington University in Oregon. Coming back to Frankfurt, this is when many of us met you, because Professor József Zimányi and Judith Németh, they had very strong connection with the Goethe University and the Nuclear Physics School, where you were one of the basic person of these fields and developing high-energy nuclear physics, heavy ion collision, properties of the strongly interacting matters and extreme fields. It's very interesting to look back generally 50 years when this field started to bloom and how quickly it was raised and it became widely visible, very interesting, and how the young people were attracted. I was every time amazed at how many young people were studying and working on this field in Frankfurt. And after that, you choose the freedom. You moved to the United States, where you became professor of the Duke University. And this was also the place where you were, I would say, among the many other clever people you remembered on your Hungarian connections. And Tamás Bíró was working long time with you. It was also my privilege to have 1 year postdoc position, and we study and work many interesting question of the early universe, how quark-gluon plasma produced in proton antiproton collision. So it was a very great time, and I think all of us just remembering very positively, and the years at Duke under your supervision, under your professorship, gave a big push, many of us here in Hungary. You became the dean of the Natural Science Faculty in '99, and after that, how would I say, fulfill this mission. You became the head of the Duke University Theoretical Studies and Mathematics Center. And what is even more bigger responsibility was when you became the vice director of the Particle and Nuclear Physics Laboratory of the Brookhaven National Laboratory. And I think, let me say that you did a great job, because Brookhaven was really is a center of high energy physics, and many of us, we really appreciate that you took this position and you drive the scientists in Brookhaven into that direction, which helped the field to flourish and really to become a very attractive, a very fruitful, and a very challenging field of the theoretical physics and experimental physics. You wrote a couple of books. I think one of the book which you wrote in 1983, this was the physics of the quark-gluon plasma. This was a summary of the field in that time. That was also a very useful, I would say, manual textbook for the next generations. And I am telling this because many young people are sitting here, so please go to the library or go to the network and browse. You will find treasures there on these books and on these papers. Berndt wrote numberless, so 340 scientific publications. It was 45 summary publication and 10 book. So I think this is really a great achievement, and you are forever young, so we are looking forward for the other produced papers and books in the near future. So I think let me phrase in that way that it is really our privilege and here in the Hungarian Academy of Sciences that you were willing to join to the Academy and to become the honorary member of our Academy. And I hope that you will also like and support this idea and our connection with you. This will be a next step in the next years, and also to see the young people. So I hope that you will learn a lot in the next years on the achievements of Professor Berndt Müller. So please give your advice and your summary on this exciting field of the quark-gluon plasma physics and high-energy nuclear science. Thank you very much for coming and to give this talk.
So thank you very much for this very kind introduction. A famous American movie star, Groucho Marx, once said, "I would not want to belong to any club that would have me as a member." This is not true for the Hungarian Academy of Sciences. I feel extremely honored to be an honorary member of this very historically important and institution with a great tradition. 200 years is quite an achievement, and so I feel tremendously honored by this election. So thank you very much. What I would like to do today is give a little bit of an overview of how the field to which I had the fortune to contribute a little bit over the past 50 years developed, where we are now, and what are some of the exciting questions that are now being asked and for the future. Let me briefly also mention, Peter, this book that you mentioned, The Physics of the Quark-gluon Plasma. It was actually mostly written here in Hungary, because I was going to the Balaton conference, and in the afternoon we were at Lake Balaton. There was not much to do. Some people were swimming, the sun was shining, and I was sitting there, and I actually wrote most of the chapters of the book there. It was very inspiring scenery and a great atmosphere. So there's a lot of connection to Hungary, and you will see some more later on. So the years in the mid-1960s saw a number of revolutions in science. They were really mostly experimental discoveries. The first one was the cosmic background radiation in 1964, technically, which showed for the first time conclusive evidence. It was speculated before, of course, by people like Gamow and collaborators, but it showed conclusive evidence that the universe was born hot and that it had cooled down over billions of years. The other discovery, about a year later, was that by Hagedorn, a physicist at CERN, who concluded from the experimental evidence that actually the spectrum of hadronic states grows exponentially with energy. And that had a tremendous consequence, because if the spectrum of states grows exponentially with energy, there's a limiting temperature. And if that is really true, the universe could not be ever been hotter than this temperature limit. And finally, there was the discovery of neutron stars, which showed that you could actually have gigantic sun-size nuclei in the universe. And the density at the core of neutron stars was known from just theoretical calculations to be much bigger than normal nuclear density, and the question was, what actually is the matter at the core of neutron stars? So this really led physicists to speculate a lot about what matter is at the highest densities and highest temperatures. But the real breakthrough there came about 10 years later, when quantum chromodynamics was discovered as the theory of the strong interactions. And immediately after that, in the mid-1970s, there were 3 papers that said at the highest densities, the highest temperatures, nuclear matter is actually composed of quarks and gluons that move around without being bound into nucleons or mesons. One was the paper by Collins and Perry that really talked about the matter at the core of neutron stars. There was a paper by Cabibbo and Parisi, who said that the Hagedorn temperature may not be a limiting temperature, but actually a temperature of a phase transition to a new matter, to a new state of matter, which is a quark-gluon plasma. And finally, Shuryak, a year later, pointed out that the mechanism to produce a quark-gluon plasma was really to collide nuclei or protons even, but it is the gluons that interact that make a hot state of matter. So by the end of the decade, scientists identified a direct way of actually probing this, namely the collisions at high energies of nuclei or even protons. And so the question was how to do this. Before we go there, let me cover a few concepts, basic concepts for those of you who are not nuclear or particle physicists. We have here today the standard model of elementary particle physics, a whole zoo of quarks, 6 different quarks, 6 different leptons, electrons, muons, neutrinos, and so forth. But only a fraction of these particles play a real role in the physics that I'm talking about. These are the up, down, and strange quark, and their antiparticles, and the gluon. So there is a certain subset of particles that are really relevant for the physics I'm talking about here. The basic concept then, as now, is that if you take matter composed of protons and neutrons, which are bound together into, have quarks that are bound together into states, and you squeeze it or you heat it. At some point, you break up the bond, and you get matter that is more like a plasma in terms of the strong interacting force, which has freely moving around quarks, antiquarks, and gluons, the quark-gluon plasma, which is characterized by temperature and a quark chemical potential or a quark density. The basic concept very early on was that because there are many more free degrees of freedom in a quark-gluon plasma, if you count all the quantum numbers of quarks and gluons, than you have for nucleons or for the lightest mesons, pions, the pressure of a quark-gluon plasma is rising much more rapidly than that of normal nuclear matter if you increase the temperature. At the same time, at zero temperature, nuclear matter is more stable. So you have here a case of a red line that rises rapidly but begins actually at a negative pressure, an unstable state, and then it eventually takes over, and the preferred state at high temperatures is the quark-gluon plasma above the hadronic matter. In these early days, the idea was that this is actually first-order phase transition. We now know that it is not. We even know that it's not a phase transition at all. It is just a very rapid change from one phase of matter to another. But nonetheless, this is what drove the original ideas. So from the beginning, it was clear that there were certain aspects of physics that really are different for a quark-gluon plasma. First of all, the color degrees of freedom that associated with the strong interactions of quarks and gluons lead to a rapid rise in the pressure and the energy density as a function of temperature. That's what I just showed. Also, gluons, if thermally excited, interact very strongly, actually more strongly than quarks, because they are higher charged in terms of color, and so they enhance the scattering rates and the reaction rates. Third, when you have a high density of such particles, free particles, quarks and gluons, the color force becomes screened, like in a plasma, in an electromagnetic plasma, and so eventually you will not have bound states among heavy quarks because of the screening of the color force. And finally, the dynamical mass of quarks that you see as a third of the proton mass in normal nuclear physics disappears, and only the very small mass given to up and down quarks by the Higgs boson, which is a few MeV, not 300 MeV, is left. What was initially overlooked is a very important experimental observational consequence, and that is, even though the color force is screened, the interaction is still very strong. And that means that the quark-gluon plasma is a strongly coupled system, and as such, it is actually a good liquid. It flows very well. It has a very low specific shear viscosity. On the basis of these general ideas, physicists developed the idea of probes. How do we actually see if we form a quark-gluon plasma? One was that if the mass of the quarks drops rapidly, strange quarks become actually relatively light compared to the thermal energies, and so they're easy to make, and so you should get an abundance of strange quarks and antiquarks in a nuclear collision if you form a quark-gluon plasma. Once you have liberated the quarks, and the matter cools down and forms again hadrons, then they should coalesce into bound states in a universal way. And that should happen at the temperature where this transition happens. So the spectrum of hadrons that you form should reflect that transition temperature. When you also, in the collision, form heavy quarks, they should not form bound states, and therefore the production of bound mesons out of charm and anti-charm quarks should be suppressed. The entropy, the pressure, the entropy, energy density should be very high, and it should reflect the number of degrees of freedoms of quarks and gluons and not some hadronic states. And finally, because of the increased scattering rates, if you form in the collision a energetic quark that escapes and forms a jet, that should be strongly suppressed. So these were the ideas on the basis of the principles that I just laid out. What was unexpected, and we added to this later on because of the observation, is that because of the low shear viscosity, the expansion is almost ideally hydrodynamic. And that means that the shape of the original formed state is easily transmitted in the spectrum, the flow velocity of the particles that emerge from it. So you can actually correlate the flow of particles in the final state to the geometric shape of the initial formed quark-gluon plasma. From the beginning, Hungarian physicists played a very important role. And I've just listed here a few of those who were there fairly early on and who made important contributions. First and foremost, József Zemanyi, who educated a number of the people here, but also himself made important contributions. Thomas Biro and Peter Lévai, of course, are here, two of his students. Miklos Gyulasi, Hungarian, but exiled Hungarian in America, was also one of the first people who really worked on this, and in particular wrote important papers with Peter. And then three physicists that I singled out here who worked on the rigorous calculation of the thermodynamic properties of the quark-gluon plasma using lattice gauge theory. And in particular, this was pioneered by Julius Kuti, and the final rigorous calculations that established what we know today were done by the group led by Zoltán Fodor and also Szabolcs Borsányi. So I wouldn't be talking about this here if the scientific community had not decided and advocated that important and big scientific investments were made. This happened in the late 1970s and the early 1980s. The decision to actually build and equip particle accelerators and colliders to study these high-energy collisions. At Europe, the path was you upgrade the CERN superproton synchrotron. That should give you enough energy to make baryon-rich quark-gluon plasma. And then eventually, of course, it was the decision to also use the Large Hadron Collider for such experiments, but that came considerably later, and it did not drive the construction of the LHC. In the United States, physicists were bolder. They said, let's build a special dedicated collider, the so-called relativistic heavy-ion collider at Brookhaven, to search for that state of matter. The original investments were made rather modest, but the RIC actually was a more than $1 billion in terms of today's dollars, probably about $2 billion investment. And of course, the LHC is even more expensive, but it was not built specifically to do heavy ion physics. When you make investments of that kind, then the scientific community, but also the politicians and the funding agencies say, tell us how actually you will discover the quark-gluon plasma if you make it. That's a fair question. In those days, the way that you had to answer this question was relatively lenient. Today, you have to produce book after book after book after tremendous documentation. How exactly you will do it? This would have been a problem because nobody really knew how to do it. So people came up with crude qualitative ideas, and these were in the United States put together in terms of a long-range plan in the year 1995. And there was a table of signatures that you see here on the left. What's remarkable is that this is the energy that is required to make a quark-gluon plasma, and it doesn't have a scale. If you would present that today, you would be laughed out of the room. In those days, people were excited. Let's build it. Let's do the measurements. Let's build it. Let's do the measurements. And indeed, that's what happened. Now, as I will show you in about 20 minutes or so, not all of these ideas panned out, but enough of them did to actually make this a scientific success. So, on the basis of these crude ideas, there was an experimental strategy at RIC. The community decided to construct 4 different detectors: Phobos, Brahms, Phoenix, and Star, in addition to the machine. At CERN, eventually, there are also 4 detectors, all of which now are also measuring the quark-gluon plasma physics, but only one, namely ALICE, is the one that was specifically constructed to do that physics. And ALICE actually was designed, in a sense, to be similar but more capable than the star detector. So they learned from what actually worked at RIC. So what you see here is a phase diagram. I talked about initially that quark-gluon plasma is characterized by temperature, that's shown here on the vertical scale, a nucleon or baryon density that's shown on the horizontal scale. So in this two-dimensional plot, RIC explores that light blue region, and the LHC explores a very narrow but very large, extended in the vertical direction region. So this covers a big area in that phase diagram, in particular, a large fraction of what is potentially interesting. There is a domain further to the right and maybe a little bit down, which is potentially also interesting, where there may be a phase transition, a critical point in the phase diagram. This hasn't been seen yet, and maybe the FAIR facility in Germany, if it eventually starts operating, will explore that. This shows now where in the phase diagram you actually are. What are the energies that bring you into the domain where a quark-gluon plasma can be formed? And what you see on the lower left is the region that you could explore at the CERN superproton synchrotron. It just barely reaches it. Now, today, we believe, yes, it did form the quark-gluon plasma, but by being in such a narrow corner, the evidence wasn't very convincing. RIC covers a very large part, so it was well designed from that purpose. And most of these blue points are measurements in terms of the energy density compared to the beam energy made from RIC. And then the red point up there is that from the Large Hadron Collider, which is more than a factor 10 in energy to the right. And a biggest part of the confirmation that we really understand the physics comes from the fact that the prediction based on the blue points hit the right point, and the measurement's there. That's a big extrapolation, and only if you understand the physics pretty well can you rely on making that happen. So let me go through a few of these signatures now. The first one is strangeness, the abundant production of strange quarks. That was a calculation that was done partly by Thomas Biro and Zimandi, by Rafelsky and myself in the early 1980s. And this was spectacularly confirmed by the experiments at CERN and LHC and RIC. And you see that as you increase the size of the fireball, the production of these strange particles, even those that contain multiple strange quarks, goes up tremendously by factors of 30 or so. So that was a tremendous confirmation. The suppression of heavy quark bound states on the basis of if you make a dense quark-gluon plasma, the color force becomes screened, was predicted. It was seen to some extent, but the surprising thing that happened at the Large Hadron Collider on the right-hand side is that actually the production of these charmonium particles goes back up. So why does it go back up? Well, it turns out that if you make enough charm quarks and then you cool down and recoalesce the quarks, you actually make more charmonium particles than you would if you wouldn't go through a quark-gluon plasma. And so, although this shows that the charm quarks originally were liberated, it is contrary to the original predictions, but still confirms the idea of color screening. The critical temperature, originally Hagedorn temperature, is a transition point from quark-gluon plasma to hadrons, was confirmed by looking at the chemistry of all the spectrum, the abundance of all the hadrons that are produced. And the experiments measured a great deal of them, and you can compare them with the abundance, the yield they expect by production from a thermal state at the critical temperature, and you find that they all agree very nicely. You can actually analyzed this in great detail using different ways of making the analysis. And from that, we now know where that transition region is. And on the right-hand side, you see that phase diagram, baryon chemical potential on the horizontal axis, temperature on the vertical axis. The blue line with a region around it that gives you the rapid transition region. That comes from a lattice calculation by Fodor and Borsani and others. And that's where the experimental points lie. So in other words, there is perfect agreement between theoretical calculations of the thermodynamic state where the transition happens and what the experiment tells us. A very remarkable success. Finally, suppression of jets. Because of the strong scattering of an energetic quark as it goes through the quark-gluon plasma. And here, first the experiments at Brookhaven, but then later at the LHC, even more impressively, showed suppressions of the factor of about 5 to 10. So that is universal, that's seen everywhere. And from that, we now know what the scattering cross-section of quarks inside the quark-gluon plasma is. We don't know yet how to calculate it as precisely as the transition temperature, but we can analyze it from the data, and we have a 20% uncertainty from the experiment of that point. I mentioned in the beginning there were some phenomena that were not predicted, but that turned out to be very interesting and very revealing. And one of them is the collective flow. It turns out that when you collide nuclei, but they don't hit head-on, but they hit at a certain impact parameter, the region of matter that you produce is obviously geometrically this kind of elongated shape. It's longer in the vertical direction than in the horizontal direction. And if you have a state that is hot, strongly coupled, under its own internal pressure, it expands primarily in the horizontal direction because that's where the pressure gradient is larger. So you expect that the geometry is converted into a flow anisotropy, and that's exactly what you see on the plot on the right-hand side. From the amount of anisotropy that you see, you can deduce how fluid the matter is, how low is the shear viscosity relative to its density. And the diagram down here in the middle shows where the quark-gluon plasma is in that ratio compared to other materials that are typically probed, like water or helium. It is indeed by now still the matter with the lowest specific or kinematic shear viscosity that we know, actually close to what we call now the quantum limit. If what you produce is not just a smooth drop, but has internal fluctuations, and nuclei are finite, so you expect fluctuations of density inside the collision from event to event, you should also see them as fluctuations of not just the elliptic shape that I showed you before on average, but also triangular and square and quintangular, whatever you say, a different kind of shapes of flow. And they agree extremely nicely with the calculations. Again, this is a double check on the viscosity, which is in very nice agreement. And finally, a prediction that was originally not in that form, but conceptually made by Biro, Lévai, and Zemanier in, when was it? 1995, I think. 1995.
Between that and 2000.
In the 1990s, was that when the quarks cool down and form hadrons, they coalesce in particular forms, and you can make those predictions. The flow added to this that you could not only predict how these hadrons formed out of quarks form, but also how they will then flow as hadrons, reflecting the quark flow in the original plasma. And so that should be independent of the hadron, just reflecting the flow of the quarks. And that's indeed what was seen in a nice experimental way. So that confirms this coalescence or recombination model. So let me go back here. These were the original 8 signatures. The green ones worked out. The yellow ones worked out so and so. They had to be modified, but you could still say they worked out reasonably. The two red ones were not seen, and we now know why, because the assumptions underlying them were not true. They required a phase transition, a real phase transition, and that did not happen. But in addition, we had a number of signatures that were not originally predicted that are in excellent probes now of the matter and from which we have learned a lot. So we have a number of textbook results that I've listed here, but in particular, the quark-gluon plasma is really a quark-gluon plasma. It is the quarks that flow, the gluons that are active thermodynamically, we know that, and it is a strongly coupled relativistic plasma. There are many open problems. From the point of view of my own interest, there are two that are foremost. The first one is one on which very few people work now. Actually, I know nobody who really works on it, although I think it's a totally unsolved problem. In chemistry, in condensed matter physics, the way you understand a liquid is that you have a system of particles that interact strongly. It has an attractive force at large distances, and it has a strong repulsive force at short distances, which keeps particles from squeezing together. In the quark-gluon plasma, you don't have a repulsive potential. It just isn't there. It's always an attractive force. So why is it a liquid? What is the appropriate theory of a relativistic liquid without a strong repulsion? We have no idea. Nobody has presented a convincing theory of that. I think that's a very interesting question. But again, I don't know of anybody who's really working on this right now. The other open problem is we think normally of liquids and states of matter as big systems containing many particles. So how small can a quark-gluon plasma be and still be called a quark-gluon plasma? Originally, people wanted to collide gold nuclei or lead nuclei because they thought you need big systems to make a new state of matter. But what we've learned over the last decade or so is that if you take smaller and smaller and smaller system, you still see exactly the same physics. On the left-hand side, it's the size of the fireball, basically, the inverse size of the fireball, the number of particles in it. It goes down and down and down, and everything looks completely smooth. On the right-hand side, you see data from CERN, CMS. On the right-hand plot is for lead-lead. The left-hand plot is for proton on lead. That's tiny compared to a lead-lead system, but still, it shows you essentially the same physics. So a single proton colliding with a nucleus is able to produce basically a quark-gluon plasma. How is that possible? What does it mean? At RIC, this has been probed by colliding protons, deuterons, and helium-3 nuclei and gold, and the specific structure of proton versus deuteron versus helium-3 shows up in the final state as flow pattern. So what's going on here? As a matter of fact, Peter mentioned that. In 1991, when Peter was there, we looked at data from, at that time, the tevatron, proton-antiproton collisions, the most violent collisions available at the time. And we concluded by theoretical calculations that the only way we could understand what they were seeing was the formation of a quark-gluon plasma. It got published, but it's also clear that we were very careful in how we phrased that, and mainly due to detector limitations, I think it is also clear at that time, there was no convincing evidence that could prove this beyond a reasonable doubt. So the proof required higher energy, higher luminosity, and detectors capable of producing very high statistics data, much higher data rates. These we have now, and these give us the results that are showed on the previous slide. So we now know this actually does happen. Most recently, CERN has collided to check that if you're between protons and lead or gold, take a nucleus that's much smaller, that is somewhere in between, and they collided oxygen on oxygen and neon on neon. Now, when you go to small nuclei like this, they all have idiosyncratic shapes, right? You can think of an oxygen nucleus as some combination of 4 alpha particles. It's not just a round nucleus. And neon even is a very weird nucleus with an oxygen center and then another alpha particle around. So these have very specific shapes. And what you find is that actually you see remnants of that shapes in the flow that comes out of the quark-gluon plasma. So in other words, we now have the ability to probe this change of physics over very large changes in size of the system from proton to the heaviest nuclei. And we're finding an increasing thing. So on the theory side, the question is what does it mean to have a system of a proton size that's still like a thermal piece of matter? And I don't want to go into detail here, but how does a system that is not in connection with a heat bath thermalize? And there's been a tremendous amount of work on this in condensed matter physics over the last, statistical physics, I should say, over the last 30 years or so. And the understanding now is that if you have a strongly coupled system, a quantum system that's in isolation, that is in an energy eigenstate, and you probe it locally, then you find that actually its properties look thermal. That is called the energy eigenstate thermalization hypothesis. Until recently, it was a hypothesis, because in order to prove it, you have to do exact quantum calculations of complex, chaotic quantum systems, and only modern computing power has made that possible. And so one particular aspect of this is that if you take a subsystem of a bigger quantum system, even if it's still a small quantum system, but a subsystem, you look at that, and you make it larger and larger and larger, then initially what one calls the entanglement entropy, that is the uncertainty in information that this subsystem shares with the rest of the system, grows with the system size until you reach half the total system. And if you make it bigger, then you'll find that eventually you actually have a pure quantum state, and that entropy goes back down. So in other words, the thermal entropy as a function of the subsystem size would show a volume law and grow, but the true quantum mechanical entropy, after half the size, falls back down to 0, because when you measure the whole system, you have a pure quantum state and 0 entropy. In order to show this for a quantum system that you study, you need to be able to solve that on a computer exactly for thousands of quantum states with exact calculations. And we've done this recently for a system that's a simple model of a lattice gauge theory. And indeed, what we find is exactly this behavior. That's called a Page curve, because the guy who first proposed it is on Page in the 1990s, but that was on the basis of assumptions, a proposal. We now can actually do a calculation. We can't do it yet for real QCD, but we should be able to do that soon as computing power increases and sophisticated methods come up. Let me stop this and just say a few words. Of course, progress really depends on experiment, as we have seen. And so I'm very optimistic that this will continue. In particular, at the LHC, there's a proposal to build a completely new detector that's much more capable, called LS3, which will use the most modern detection techniques, in particular silicon detector technology, to now really cover the whole physics of charm quarks and bring charm physics as probes into the same capability as light quarks. There's also the focal, let me mention, how do I go back? Yeah, there's also the forward calorimeter that will probe not the quark-gluon plasma directly, but it will probe the gluon component of nuclei and protons that is thought to be the precursor. That was Juriek's idea in 1976, but still not really proven. The idea that this is the gluon component is responsible for the formation. So hopefully that will be built and will explore that physics. So in summary, the search strategy for the quark-gluon plasma, although very nebulous in the beginning, turned out to be very spectacularly successful. Many of the predictions were confirmed. Some needed modification. And some very speculative ideas turned out to be wrong. But that's to be expected. Now we have established the existence of the new phase of matter with beyond any reasonable doubt. There are too many experimental evidence that clearly show it and that actually are in excellent agreement with theoretical predictions. So what have been the main foundations of these discoveries? When you think about it, there are a number of them. First of all, the experimental facilities that were constructed were very versatile and carefully designed. Number two, the scientific program was also comprehensively designed, and there were enough experimental attack angles that provided a comprehensive picture. There was a continued improvement in the detection capabilities over the last 30 years due to partly technical progress, but also better understanding of what needed to be measured. And there was an increasing precision in the theoretical predictions and the theory data comparisons. Technology does not stand still. We know we now have we are able to build much more capable detectors. Hopefully we'll have quantum computers that are capable in the future. And so from both experiment and theory, I think we will see tremendous progress over the next 20 years, 30 years, 50 years, who knows? But the field looks bright and the future looks bright, and I'm sure that in a few years from now, we will know a lot more than we know today. So thank you very much for attention. I appreciate it.
Thank you very much, Professor Müller, and my honor and my duty is to handle you, and I will ask Peter also to come to help me to give you the diploma, or how we call this, and officially you became the honorary member of the Hungarian Academy of Sciences. Thank you very much.
Thank you very much.